Welcome to yet another session of Problem Stats 1, that is MA 176. Now, in this section, we shall be looking at some basic laws governing set theory. Now, these are laws that we are already familiar with. With these laws, we shall be talking about the commutative, the associative, and as well as distributive, and some others which we shall be looking at very soon. So once we are talking about the commutative law, remember from our senior high school days, once we are talking about commutative, it's more or less like the addition of two, let's say, terms is the same, their opposite also what holds. So in that same case, just as we had a plus b is equal to b plus a, once it comes to the set theory, same rule also applies here. So in any case where we have two events, let's say A and B, all that the commutative law says is that event A union B is equal to event B union what A. Now once such a situation happens, it means that these two events obeys the commutative law. Now same thing can exist for their intersection, where we have A intersection B is equal to what? B intersection A. So it means that anytime we should have an event or two events, anytime we should find their union or their intersection, if we should turn them the other way around, we are still going to get the same one outcome. Okay. We also have the associative law, and remember from the associative law, anytime we should have let's say A plus B or into bracket plus C is the same as A plus B, then B plus C or into bracket. Now same thing happens here once it comes to their union and that of what their intersection. So you can see that A union B, that is into bracket, or union C is the same as what? A union B union C or bracket. The same thing exists for the what? Their intersection as we have here. That is A intersection B, bracket close, intersection C is all is equal to what? A intersection into bracket B intersection what? C. So in this case, to once it happens, so it means that they do obey the associative law. Now let's talk about the distributive. So in case where we have A union B, all intersection C, this will be the same as the distributive law, where we get to multiply the elements in here by the outside what term. So this will be A intersection C, B intersection what? C. Similar fashion, we could have A intersection B or union C, and this is just as we did earlier. Okay, so A union B, B union what? C. Okay. So now let's look at another interesting one called the De Morgan's law. Now with this, De Morgan's law talks about their complement. So anytime we should have two events such as A and B, and we have A union B or complement, this is the same as what? A complement intersection B what? Complement. Remember the operation here what changes. So remember that. Now, if we should have A intersection B or complement, this is the same as what? A complement union B complement. And remember these signs too. They change once it comes to what? Multiplying by what? Their exponent or raising to what? Their powers. Okay. So keep that in mind. Now we could also talk about a disjoint union. Now with this disjoint union, this is another extended form of what? The union between two events. So anytime we should have two events, their union will be the same as what? A intersection B and C, or B complement or union, A complement intersection B, then union of what? A intersection what? B. Okay. Now all these are what? Disjoint sets at the end of the day. So now with this, let's look at some interesting probability axioms and some properties. They are very important ones, and these are some basic properties that we have to know before we can perform any probability. Now, given an experiment and a sample space S, the objective of probability is normally to assign any event a number called P of what? A, called the probability of what? Event A. Now, remember from the initial session, we did talk about statements that are normally probability in nature. The probability that, let's say, MA1 will win the Vice Chancellor's Cup. Although we are just going to say this in a literal way, but in such situations, we are hopeful, or we always expect to assign a numerical value to this kind of what probabilities that we are making. So if you can say that UMath, or let's say the mathematics department team, has, let's say, a 90% chance of what winning the Vice Chancellor's Cup, then it will make more meaning. So for any probability that we shall talk about, it's always best, or it's always our objective to always assign a numerical value to these probabilities. And for us to assign these numerical values, we must get to know of what these three axioms, which all these probabilities should satisfy. So let's look at the first axiom, that is axiom 1. Now, with this axiom 1 implies that for any event A, the probability of that event A should be greater than or equal to what? 0. Now, this event is all about reflects the intuitive notion that any chance of occurrence should be a non-negative number, meaning that all probabilities shouldn't be negative. They should start from 0 onwards. So in this case, there is no chance that we shall be dealing with negative probabilities. So if you should come up with a probability someday, this probability shouldn't be negative. It should be positive. Now let's look at axiom 2, that is the probability of the sample space. And remember, the sample space consists of all the elements from an experiment, or the possible outcome of an experiment. So axiom 2 is just trying to say that the probability of the entire sample space should be equal to 1. So that is to say that all the events, or all the outcomes that we have in the sample space, if we should find their probabilities, all of them should give us 1. Now this is also trying to say that the maximum possible probability of 1 is assigned to S. That is, the sample space is defined by the event that must occur within the experiment, and its performed contain all the possible outcomes, just as we defined for the sample space. Now let's look at axiom 3. Now this axiom 3 says that suppose that we have an event A1, A2, and A3 is an infinite collection of disjoint events. Then the probability of event 1 union event 2, or all of their unions, all should sum up to probability of the A. And with this one formalizes the idea that if you wish to obtain the probability that at least one of these numbers can be simultaneously, then the chances of one occurring is the sum of all the individual elements. Now this that we see is going to result for countably infinite number of terms. Now this might be a little bit controversial, but as we move on, we are going to really understand as we try to take some examples of this kind of axiom. We are going to see really what goes in there. So that is to say that with this axiom that we have, they can be grouped into about a number of properties. So anytime that we should have a probability and we like to determine the probability of its complement. So suppose that we've been able to determine the probability of an event, let's say A, and we like to determine the probability of that event's complement. Now remember that all probabilities should range from 0 to 1. So if this A complement refers to anything that is not located in the event A, it just suffice to say that the probability of the A complement is just equal to 1 minus the probability of A. So in this same case, if we should have, let's say, a probability of A equal to, let's say, 0.7, now the probability of A complement should be equal to 1 minus 0.7. and probability of A complement is going to give you a 0.1. Okay? So if you like to determine the complement of any event, it's more or less like estimating for the probability of that event and just subtract it from what? 1. Now property B says that the probability of any null event is equal to what? 0, and this makes sense because the probability of nothing is equal to what? 0. Now for property C, that is if A is a subset or a member of what? B, then probability of what? A should be less than or equal to probability of B. Now remember that if A being a subset implies that A is some component or some of the subset that have been taken out of what? B. So if we are to calculate for or estimate the probability of A and B, it means that definitely the probability of A should be lesser than or equal to what? The probability of what? The bigger set. Okay? Because A happens to be the smaller set and B happens to be the bigger set in which A was taken from. Okay? So definitely the probability of A should be less than what? The probability of what? The bigger set one B. Now probability D happens to be the addition law. This says that probability of A union B is equal to probability of A plus the probability of B, or minus the probability of A intersection 1 B. Now let's look at this. Suppose that we were to draw this on a Venn diagram. My Venn diagram is not perfect, but let's just stick to this. Now suppose that we have our probability, that is event A here, and this side happens to be event B. Now let's see how we get to what? Sum these two events together. Now if we should add the whole of what? This event, remember the whole of this is event A and the whole of this is event B. Now if we should add these two events together, now you can see that there is some sort of what? Overlapping in here. Now if we should allow this overlapping to just maintain, it means that there is going to be some sort of what? A double counting in here. Now to cater for this double counting, that is why we get to what? Subtract their intersection from this union that we are trying to create. So that this is just going to take away what? Just going to negate that duplication or overlapping that we have here. So that is why normally we get to what? Negate their intersection. Now this probability or this property holds in cases where the event is not mutually exclusive, meaning that their intersection or they have something in common. Once this happens, it means that this probability or this property D of addition law will what? Will hold. Now we shall look at a situation whereby the event is mutually exclusive, where we are going to just neglect this portion, but that is something that we are going to look at very soon. Now with this, let's see the true implication of or how we are going to interpret these probabilities, that is on a basic level. Now remember that probability starts from 1, 0 to positive 1, 1. In between we have 0.5. Now anytime you should have a probability value within this region or getting closer to 0, this implies that the event is very unlikely to work. The chances for that event to occur is very small. Now if it is exactly 0, it means that that event is not going to at all. Now if you should be approaching 0.5, it means that the chances of the event occurring is just likely as unlikely. So it's more or less like the chances of that event occurring is not so clear. It's like it's likely or not likely, more or less like in between. Now if you should have something approaching positive 1, it implies that the event is most certain to 1. But if it is exactly equal to 1, it means that that event it was surely 1. So this is how we get to interpret our probabilities on the basic level. But let's try to take some real life example to see how we get to do that. Now consider the tossing of this thumb tags as we have right here. Now with this thumb tag, consider that we are throwing this in the air. Now when it comes to rest on the ground, there are two outcomes, whether it's going to point up or it's going to point downwards. Now if it should point upwards, we are denoting it by U. but if it should point downwards, we are denoting it by what? D, okay? So this implies that the sample space, the possible outcomes is what? U and what? D, as we have in here, okay? Now, the axioms specify that probability of the sample space is equal to 1. That is to refer that if you are to estimate the probability of this sample space, it's definitely going to give us 1. Because whenever we throw the term tag, definitely something is going to occur, one of these, and we are going to look at taking them one by one. So if we are to look at the probability of this whole sample space, this should give us what? 1. Now, for the second one, since U and D are disjoint, then their union is S, then the foregoing proposition implies that if we like to estimate their probabilities, okay, or the probability of S, which is equal to 1, this will be the probability of the event U and the probability of what? The event what? D. Now summing these two should give us what? The probability of what? The sample space, which definitely is equal to what? 1. Now let's look at more stuff. But if we should be dealing with this event what? Singular, like throwing it for the first time, definitely it's either we are going to get a point up or a point down. Now, because these two positions have equal chances of occurring, it means that their probabilities will be half of 1, which is the same as 0.5 and 0.15. So probability of the thumb tag facing upwards is equal to 0.5 and facing downwards is equal to what? 0.5. But in cases where it's likely that one position is likely to fall than the other, it means that that position or that event would have more probability over the others. And whatever you do, because there are just two events, the addition of these two events should just give us what? 1. It shouldn't be more or less than what? 1 in this case. So if we should have 0.75 here, the other outcome should give us what? 0.125 to be its probability. Now, suppose that we let P represent any phase number between 0 and 1. That is, the probability of U will be equal to P, and the probability of D will be equal to what? 1 minus P. And remember, this satisfies the axiom 1. That will be the axiom 1. Remember that if you are able to estimate one part of it, determining for the other part is the same as what? 1 minus the other part, okay? Because probability, all of them should sum up to 1. So if you are able to calculate the probability of one side of it to be P, then it means that for the other side, which is the down, should be equal to what? 1 minus P. And this is consistent with what? The first property that we dealt with. Now let's try to look at another example involving testing of car batteries. Now consider a testing batteries coming off of an assembly line one by one until we have a voltage within a prescribed limits. Now in this case, suppose that we do have an assembly line. Remember, once we are dealing with assembly lines, it means that we have objects on them and these are just governed. Now with this case, we like to look at a situation whereby within the assembly line, we are just going to monitor it until a battery having a voltage within a certain prescribed limit is found. Okay. Now, for this event, it implies that if we should have a success, or if we are able to indicate that this particular battery or series of battery is good, then we are going to represent it by S. But if the battery at under consideration, or a battery at the assembly line at a particular point happens to be beneath that prescribed limit, then we term this to be what? F, meaning more or less like what? Failure. So in this, it could be that the first battery that comes off the assembly line will be within the prescribed limits, which in this case, it means that the first event is what? Is successful. Now it could be that the first battery will be faulty, but the second one might be what? Within the prescribed limit. So we could also have events failure and that of what? The success. We could also have event failure where the first two batteries will be faulty, but the third one will be successful. And this can continue to infinitesimally many what events. So this can now Suppose that the probability of any particular battery being satisfactory is 0.19. This can be shown that the probability of event 1 is equal to what? 0.9099, and we are going to see how this is being done. So sorry, this is supposed to be just 0. So this is equal to what? 0.199. There's no 0 here. So if you would like to look at the probability of the second event, and remember the second event was just what? Probability of what? F, outcome F and X, okay? So if you would like to look at this, it means that for us to get, we have the probability of a success being equal to 0.99. So with this ideology, for us to get our probability of failure, this will be equal to what? 1 minus probability of success. And remember, our probability of success was equal to what? 0.199. So this implies that our probability of failure is equal to what? 0.01. So that is how we get to determine this. Now, so for event 2, because this comprises of failure and what? Success, we could just find the probability of event 2 by multiplying the probability of failure times the probability of success. And remember, probability of failure was equal to 0.01 and that of success was equal to 0.99. So that is going to give us what? The probability of event 2. Now let's look at probability of event 3. Now remember, for event 3 we had 2 failures and that of what? A success. And this is just represented by probability of failure squared, because we had what? 2 of them, times that of what? Probability of success, and that is going to give us the probability of event 3. Now I would like you to guess for the probability of what? Event 4. Okay, and with this event 4, it's just similar to what we've been doing. So this is just going to be 0.01 raised to the power 3 times 0.1099, and that is going to give us what? The probability of event what? 4. Okay, now this can continue until we have the future. So that is how the last property, that is what the last property is trying to say. If you should have an infinitesimal countable number of what? Terms or outcomes in such cases as we are having in the case of what? This battery testing, we could go with this approach to estimate what? These probabilities. Now let's look at, before we end this whole thing, suppose that we like to what? Estimate the union between all these events, that is event 1, 2, 3 up to what? Infinity. This will be the same as what? The probability of the first event, the second event up to what? Infinity. And once we have this, remember, all these events have a success in common. So if we are able to bring out what? The success from all these common terms, then we are likely to have S into brackets, that is the first event, plus this for the second event, and for the third event we have F squared plus that for the 34th event, then this continues until what? Infinity. So once we bring this out, we already know the probability of success, which we have to be 0.99, and the first term is only S, so once we multiply it by S, it's just the same thing. Now if we should multiply S by this next term, that is SF, that is just going to give us what? This event. So in this case we are just going to have the probability of the failure, which is 0.11. The next one, F squared, that is the probability of the failure squared, and this continues. So once we simplify this is just going to give us the probability of what? The entire sample space, which in all should be equal to what? 1. Now for this probability theory to be anything other than interesting pieces of abstract, there will be the need for us to do some interpretation, and that is something that we shall be looking at the next chapter. So with this chapter, the subsequent chapter or the next chapter, we shall be looking at how to explain what? these numbers that we are getting, so that everything that we are doing here wouldn't be so abstract. Okay, because remember that the main aim of this determining anything or coming up with anything is to help interpret or come up with a meaningful decision. So this ends this session, and for the next session we shall be looking at how to interpret these probabilities. So I'll see you in the next lecture.